My presentation today is on the architecture of different message brokers, right? So the other day I had an interview and I was asked like, what type of database would you use? Would you use SQL or NoSQL? And for that question, the answer is quite easy to answer. But for answering the question of which message broker should I use, it's something that you need to actually spend time to delve into the internals and really understand the key differences. And so that's what I'll be talking about today, which is I'll be going over Redis streams, Apache Kafka, Apache Pulsar, SQS, SNS, and NATs, and I'll be dissecting them, and I'll be talking about their internals, and I'll be talking about the important design trade-offs. And most importantly, I'll be talking about which message broker is the best for your use case, for your application. So this talk is for someone that's worked with a message broker, wants to learn what the other ones offer. It's for someone that wants to understand the key differences between the message brokers that you're working with. And it's for anyone that's curious about how these message brokers work internally. So before we dive in, a bit of background about myself. So I'm a distributed systems engineer. I currently work at Abnormal Security, which is a hyper-growth company in cybersecurity. So my team works on different platform services like notifications, feature flagging, RBAC, which are used across the company. Previously, I worked at a observability company called OpsRamp, which was acquired successfully by HP Enterprise. So there I got to build a couple products from the ground up. So we built a distributed log management system and a distributed tracing product. So I got to work with ClickHouse, with Golang, Kafka, Spark to build scalable log ingestion and querying systems there. So I spent a couple years there, and then before that I got my degree in computer science at UC Berkeley. Over the course of my career so far, I've also had the chance to work with several different message brokers in production, including Kafka, Redis streams, and SQS. So that's a bit about myself. So now what I want to talk about is what are the key design decisions that you need to make when creating a message broker. Now you might wonder like, hey, why is this guy talking about the design decisions when creating a message broker when I'll probably never create a message broker in my life? But the reason I want to bring this up is the key design decisions that are used to design a message broker are some of the key evaluation criteria that we can use when deciding which message broker to use, right? So I've broken this list down into about 10 items. So these 10 items are different design decisions that we can look at and we can use to evaluate the different message brokers that we're going to talk about today. So the first design decision when creating a message broker is the interface, right? So the interface needs to support fetching messages and producing messages. But within that, there's a lot of scope for design. So the API can be over TCP, like Kafka is, or Redis is, and NATS is, or it could be over HTTP, like for instance, Apache Pulsar's API is over HTTP. The communication pattern could be REST, it could be RPC, it could be WebSockets, it could be a standardized protocol like MQTT. There's different trade-offs there. And the data encoding can vary from JSON to protobuf to even like a custom binary format like Redis streams and Kafka utilize. So that's the interface, right? Second key design decision that separate different message brokers is the data storage, right? Where are the actual messages getting stored, right? Now there's two parts to this. One is the in-memory storage, and then the second part is the persistent on-disk storage. So what data is kept in memory, what data is kept on disk, and what's the format of the data? So just to give an example, we'll talk about this in detail later, but Redis streams will primarily store the data in memory, and then it can asynchronously write it to disk, right? Whereas something like Kafka is going to write every message durably to disk, and it's going to write it to it's going to write it sequentially, right, to a segment file. So there's many differences there. The third design decision is metadata. So this is something that we wouldn't think about, but it is something that the broker does need to store. So behind the scenes, right, the message broker, whether it's Kafka or anything else, it needs to store things like the list of topics, ACLs, quotas, list of brokers, and it needs to store that in a way where this metadata is available in a consistent manner across all the nodes. So like, let's say you have multiple nodes, they all need to have a consistent view of the cluster state, right? So that's why projects like Apache Zookeeper are put into use. So metadata storage is another concern. Fourth one is producer responsibilities. There's different producer responsibilities like batching, compressing, and so on. The fifth one is the consumption strategy. So is it push or pull, right? How are the offsets stored? Are they stored on the consumer side or the broker side? How can we distribute messages to multiple consumers in a load balanced way? So that's another aspect. And the sixth one, and this is actually the most interesting one that I got to learn when I was preparing this presentation, is the compaction strategy. So this is not something that I actually thought about when I was creating this, before I knew about this, but it's quite obvious when you think about it, which is like, if you have any sort of message broker, it needs to have some method to delete messages which are no longer required, right? So whether you delete old messages or you delete messages which are already processed, you need some way to either delete or archive those messages. And so you need some sort of compactor, right? So the compactor is going to be responsible for deleting those messages. But how is the compactor implemented is another source of differences between the different brokers. Okay, so we can go through the rest of these a bit faster, and then we can move on to some of the internals of the different projects. So what we've talked about so far were the important design decisions when designing a single node message broker, right? Now, let's say we want to turn this into a distributed system. So what are some of the decisions that we need to make? So there's a lot, but I've condensed it down into 4, and those 4 are the following. First one is replicating data. So obviously, if you have multiple nodes and you're storing data on those multiple nodes, you need a way to replicate the data, right? So let's say you have a leader, single leader, which is accepting the writes. That leader needs to propagate the writes to the different replicas. So this can be done synchronously, meaning the leader will write the update to all the replicas synchronously. It can be asynchronous, where the leader will accept the write, and then in the background it will replicate. Or it could be semi-synchronous, like what Kafka does, which is it will replicate to a subset of the replicas. So that's replicating data. Partitioning data. So if you have, like, let's say a Kafka topic or a Redis stream, is there a way to partition that across multiple machines? So Redis streams, for instance, doesn't support partitioning across multiple machines. All the data for a particular stream has to fit in main memory for the primary. And then other systems like Kafka, they do natively support partitioning, right? So how is the partitioning implemented, and what is the key, right? What's the partitioning key? So that's another important one. Evenly distributing load. So how can we avoid hotspots, right? Where some partitions receive much more traffic than others, and so some nodes receive much more traffic than others, right? So how can we avoid that? So, and if we can avoid that, can we rebalance, right? So that we can get rid of this issue. And then the last one is handling network partitions, which is, in other words, if a machine is down or if it's not reachable, how can we fail over the request to other machines? So there's two parts to this, right? So the first part is if a follower is down, then can we detect it? And can we make sure not to send traffic to it? And then the second part is if a leader is down, how can we perform leader election, right? How can we elect a new leader and then we can proceed? So I know this is a lot of content. Hopefully it's able to communicate it effectively, but these are like the 10 important design decisions which I feel are crucial when designing a message broker. And so we can use this as a framework that we can use to evaluate the different message brokers that we are going to talk about today. So I'll take a pause there, and now we're going to move on from discussing this to talking about our next message broker, which is Redis Streams. So I wanted to start with like the simplest, or one of the simplest, most lightweight message brokers, which is Redis Streams. Now, I think many of us may not have worked with Redis Streams. I actually just started working with Redis Streams a couple months ago in production at Abnormal. And so what is Redis Streams, right? Is it a separate service that I need to deploy, or what is it? So good question. So Redis Streams is just a separate data type in Redis. So, just as Redis has lists, it has strings, it has hashes, it has another type, which is a stream data type. So a stream data type is a append-only log. It's an append-only list, which means you can't go ahead and modify or write to previously appended data. It's stored in memory, but Redis lets you persist it to disk. So it's not that durable. Primarily, the data is stored in memory, but you can persist it to disk using a couple different mechanisms, which I'm not going to go into today. But and then it's built natively into Redis, no third-party plugins needed. Has a lot of different features, but it's also quite lightweight, quite easy to use. So life of a Redis Streams message. So I'm not going to go over all this in detail. You guys can look at the slides later, but the way it works is that you have a producer. Producer will send a xadd Redis command to Redis. So in that xadd command for producing to the broker, it's going to include the message data, and it's going to include like a key, basically, which is used for sorting the stream entries. So that's it, right? And then on the broker side, it's going to add the new data into memory. It's going to write it to disk at some point, right, based on how you've set it up. And then it's going to replicate asynchronously. And then on the consumer side, we're going to pull the messages either using xread or xread group. So xread is the most basic one, and then xread group just gives you some additional functionality like acknowledgements and Kafka-like consumer groups. So you can choose from those two. I'm not going to go into the details, but this is how it works at a high level. So this is the architecture. And then for the compaction that I mentioned earlier, the compaction is done during insert time. So this is quite interesting. Basically, when a Redis stream is added to, if there's a maximum length for the stream set up, and we append to the stream, and we've gone over the maximum length, then immediately Redis will compact, it'll delete those old messages at insert time. So it's not like a background operation. Just to go over the summary here, so I'm not going to go into all of this, but I think actually I've gone over all this. The only new things here is that Redis has like a text-based binary protocol over TCP, which is called RESP, and internally the stream is implemented as like a radix tree. It's like a trie, if that's useful at all. So I think we've talked about this. So asynchronous replication from primary to replicas, and Oh, this is an important thing, which is Redis cannot shard one stream across multiple nodes. So the whole stream must fit in the primary node's memory, right? So that's like a constraint. So you need to rely on like vertical scaling, basically, for scaling your Redis stream. Okay, what trade-offs does Redis streams make? On the plus side, it's very lightweight. It's very easy to work with. On the downside, the durability story is not quite there. It can lose data unless you f-sync on every command. Also, it doesn't horizontally scale well, as mentioned, because if you have a stream which is too large to fit into memory, you will need to partition it on your own, right? You're gonna need to manually shard it. But then if you do that, then you're gonna lose the ordering guarantee that Redis has. So yeah, so that's just some of the trade-offs with Redis streams. So I think that's enough for Redis streams. We can move on to Apache Kafka. So, all of us are, I'm sure, familiar with Apache Kafka. So I'm not going to go into really what Kafka is, but what I want to talk more about is like, what are the key design decisions that Kafka makes, which differentiate it from some of the other brokers that we've mentioned so far. Life of a Kafka message, starting with the producer. So the producer is going to have a list of the Bootstrap servers, like basically the Kafka hostname. It's going to store in its memory broker partition mappings. So it's basically going to have an understanding of what brokers have which partitions. So that is going to do in the background. So then when you produce a message to Kafka, it's going to serialize it, right, using like Avro, Thrift, whatever you want, and it's going to add it to an in-memory buffer, right? So when you produce a message, it'll serialize it, add it to an in-memory buffer. Once the buffer size reaches a certain level or a certain time period passes, then the buffer will be compressed and it will be written to the broker, right? So it'll identify the partition, it'll look up the broker based on the mapping that I mentioned earlier, and then it will write the message to the broker. And then there are several different compression options you can choose, right? I'm not going to go into that, but that's how the producing works. One other part that I didn't know about until recently is you can set the acknowledgements, right? You can set the AX setting. So what will happen is if you force the producer to wait for a certain number of AX, then it's going to wait for that number of AX. So if the producer doesn't get acknowledgements back from any writes, then it's going to retry, right? So if you tell the producer, hey, we need to have an acknowledgement from all the replicas and it doesn't get the acknowledgements, then it's going to retry. So you can configure that as well. So that's basically the life cycle of a producer. And then life cycle of a broker. So once the broker has received messages, right, what's it going to do? So it's going to identify the current partition or like the partition that the messages are for. It's going to find the active segment file. Basically, it's just a file on disk. It's going to find the file on disk, which has the data for the partition, and it's going to sequentially write the messages into that segment file. And then also, it will also update some like index files as well on disk. So, okay, so the first step is the broker will get the message batch, and then it will add to the segment file. It'll write to disk. Second step is the broker will replicate the message to a configurable amount of replicas. So, it can write in the, least durable case, it will just write to the local disk and that's it. Or it can write to all the replicas as well. So then we're going to have replication, which is configurable. And in the background, on every broker, it's going to be running compaction. So based on whatever log retention policies you've set up, there's going to be some log cleaner threads, which is going to be continuously compacting and cleaning up the segment files, reducing the size of the segment files. So that's what the broker is doing. I'm not going to get into the consumer right now, but the summary is that Kafka has a special topic called consumer offsets. So in that topic, it's going to be storing the offsets for each consumer. And yeah, and then you have consumers which are going to consume message batches, decompress them in memory, send them to the application, and then send back acknowledgements to Kafka. Basically, they'll update the offset. So that's how the consumer side will work. So yeah, I think that covers the architecture of Kafka. I think honestly, a lot of us probably already knew a lot of the architecture of Kafka, but it's good to know some of the details. I think for me, what's helped me is knowing about like the life of a Kafka message, right? So what I went through today, that helped me a lot in understanding the Kafka internals. So yeah, just a couple other small callouts which I found useful. So Kafka has its own custom binary protocol over TCP. So it's not on HTTP. It's a custom binary protocol that they created over TCP. The brokers will store binary formatted segment files. So you'll have like a file on disk. There'll be some binary format, basically bytes, which are written according to some format for each partition. So like, let's say you have a broker with like 10 partitions, it will have like 10 different segment files that are currently being written to. And then it'll also store some like index files as well. So yeah. Metadata. So I didn't talk about metadata so far, but the reason Kafka needs Zookeeper is to store things like what are all the brokers which are available in the system, or what are all the topics. So why not just store that like in Kafka? So the reason we don't store that in Kafka is like Zookeeper gives you like the highest level of consistency. So no matter which node you read from at any time, it'll give you the most up-to-date information. So that's why Kafka will use Zookeeper to have like a consistent view of the cluster state from all the brokers. So you can look into that later, but that's the point of Zookeeper. But now Kafka has also implemented Kafka Raft, so you don't need to run Zookeeper anymore. So, but yeah, typically you would probably use Zookeeper in Kafka. So yeah, for the consumption strategy, I mentioned this, but Kafka is pull-based. So, like I mentioned, there's push-based and pull-based. Pub sub systems are typically push-based, and Kafka is it's pull-based. So the consumers are responsible for pulling the topics. You have one consumer per partition, and they're going to be responsible for pulling the topic and reading the data. And yeah, so then you have compaction as well, which is either based on time or size. So you can compact after some time has been reached or some size of data has been reached, and then you can clean up all the old data records. So you can look up the design for that when you have time. It's quite interesting. Okay, and then for multiple nodes, I already talked about this, but Kafka will replicate each partition across three brokers by default. For partitioning, you can control the partition yourself using the message key, or you can do partitioning using like round robin or sticky, right? So, but basically natively Kafka can partition for you. And then for handling network partitions, if the leader fails, then Kafka can perform leader election. So it'll perform a leader election, find the new leader for a particular topic. Actually, it should be for a partition. It'll find the new leader for a partition, and then it will update Zookeeper. So yeah, so that's how it would work. What are some of the trade-offs that Kafka makes, right? Like, it's nice to go over all this information about Kafka, but like, what are some of the important trade-offs that Kafka makes? So on the plus side, Kafka is very horizontally scalable. So like, we talked about Redis streams, where streams that are too big to fit in one machine, you'll have to manually shard. But Kafka doesn't do this. In fact, by default, all the topics are already sharded across multiple machines. It's also very high throughput. And so, if you look at any benchmark, you'll see that Kafka is like one of the highest throughput systems which is out there. And so why is this? So I'm not going to get into the details. You can look it up in the documentation, but there's a couple things. So they have their own efficient binary protocol. The producer is going to do batching and compression. So that'll reduce the number of network calls and reduce the data which is sent over the wire. And then all the writes to disk are sequential, which is like much faster than random writes. And also there's zero copy, which means Kafka doesn't actually, I won't get into the details, but basically there's something called zero copy, which means that Kafka doesn't need to copy data from the kernel into user space. It can just read data directly from the kernel. So it reduces like I/O operations which are needed. Highly durable because it writes to both disk and replicates across nodes, and it's also highly configurable. So if you look at the Kafka documentation, you'll see that there's like dozens of different configuration flags you can use to control, any aspect of Kafka that you want. So those are some of the pros of Kafka. Unfortunately, there are some downsides, which is it is pretty resource intensive because you have multiple brokers running at once, continuously writing all the messages to disk. And then also you have a dependency on Zookeeper. So because of this, you do need a decent number of CPU and disk usage. You do need a decent number of CPU and disk resources, and it can also be somewhat costly as well. So in a lot of cases, it might be overkill. And conceptually, it's more difficult to understand than some simpler alternatives. So if you just need like a simple stream, then something like simple queue service from Amazon or Redis Streams might be a better fit. So those are some of the downsides. So now we can talk about our last real message broker that we're going to talk about today. Although we'll go into some other ones at a very high level. But last one we're going to be talking about is Apache Pulsar. So Apache Pulsar, I think many of you guys have heard of it, but Apache Pulsar is a newer message broker. It was released in 2016. 5 years after the creation and open sourcing of Apache Kafka. And it promises several new features, which are quite nice. So it promises tiered storage to object storage, which is now it's available in Kafka as well. Horizontal scalability of brokers without any data reshuffling. So, in Kafka, since the data is stored on the brokers, if you want to add more brokers, then you need to reshuffle the data between the brokers, right? But in Pulsar, the brokers are stateless, and I'll get into how. The brokers are stateless. The data is stored elsewhere, so you can easily add brokers without reshuffling any data. There's a lot of multi-tenancy features, so you can like take topics, you can group them into like tenants and then namespaces, and then for each like tenant namespace, you can like control where it's like physically stored. Like you can control like what machine it's on. You can control like what rack in AWS it's on. You can isolate like certain like noisy tenants from each other. You can set like extremely fine-grained quotas. So there's like 40 different types of quotas in Pulsar. So you can set like very fine-grained quotas on like so many different things. Access control is very granular, so you can grant access to only a particular tenant, and there's a lot of other like random features like serverless functions and so on. But biggest benefits are like tiered storage, easy to scale brokers, and a ton of like multi-tenancy features. So how does Pulsar work at a high level? So I think I'm not going to go into all the details, but I will just share enough so that you can get a high level idea and maybe look into it in your own time. The key design decision that Apache Pulsar makes versus something like Kafka is that the data is not stored on the actual brokers like in Kafka, but it's stored using a separate service. So in Pulsar, the data is stored in a service called Apache Bookkeeper. So Apache Bookkeeper, it's called distributed write-ahead log system. So I honestly haven't looked into Apache Bookkeeper that much, but you can look into it. But all the data is stored in Apache Bookkeeper. So what are the brokers responsible for. So you can see in this slide here, the brokers are responsible for basically identifying the correct Apache bookkeeper node and then reading data from them, right? That's pretty much it. So all the data is stored in Apache Bookkeeper. The brokers are just responsible for routing to the appropriate bookkeeper node, getting the data, and then sending it back to the client. They also have like a cache on the on the broker nodes. There's like a cache, so that also helps speed up the data access. But the biggest thing that they do is just reading from bookkeeper and then sending the data back. So the important design decisions that Pulsar makes is that the brokers are stateless. So they're not entirely stateless because they do have some state, like the ledger cache, right? Basically the data cache. But it's not like you're actually storing the data on those nodes, right? So unlike Kafka. So it's pretty easy to scale compute by adding brokers because all the compute is done on the brokers. It's very easy to scale the compute by adding brokers, and in doing so, you don't need to rebalance any data. You don't need to rebalance anything because there's no data getting stored. So yeah, separation of compute and storage is an important thing. Another important thing is the multi-tenancy, which I talked about earlier. In Kafka, you might have like noisy neighbor problems where some partitions are very noisy and then they're affecting other partitions on the same machine, right? So let's say you have two partitions. One of them is for like a very popular user. Another partition is like for normal user. If they're on the same machine, then that machine will be receiving disproportionately more traffic than the other machines, right? So then you're going to have some noisy neighbor problems, and then you're going to have to scale it. Then maybe you'll have to rebalance the partitions, right? So in Pulsar, you don't need to do that. What you can do is you can just create a tenant, create a policy like, hey, I want you to move this noisy tenant elsewhere onto a separate machine, and it can do that very, very easily for you. So it's designed for multi-tenancy. So yeah, there's some positive aspects to it. I guess on the negative aspects, having not actually built anything with it before and not using it and having not used it hands-on, I don't really want to say anything negative about it without using it, but I guess the one thing that I do see based on the architecture is you need to run some more components than in Kafka. So in Kafka, you have the producers, you have the consumers, and you have the brokers, and you have Zookeeper. In Pulsar, you have the producers, you have the consumers, you have the brokers, you have Zookeeper, and you have bookkeeper, right? So you have a separate component for storing the data, which you will need to operate and maintain. And there's another component which we didn't talk about, which is the Pulsar proxy. It's basically a load balancer for the brokers. So you might also need to run that as well. So yeah, there's more components. Also, there's going to be a network hop needed to store any data. So you're going to need to network hop from the broker to the bookkeeper. So those are some of the trade-offs. I think overall it looks pretty good, but having not used it, I would need to see what some of the downsides are. But these are some of the trade-offs that are made. So yeah, so we have a couple minutes left. I went over a couple different message brokers in depth. So I went over Redis Streams, I went over Apache Kafka, went over Apache Pulsar. We talked about how they work internally, and we talked about some of the design trade-offs between all of them. And then in the beginning, obviously, we talked about the important design decisions that are made in the creation of any message broker. So I think that was the majority of what I wanted to talk about today, but there were a few more message brokers where I didn't have the opportunity to delve into their internals, right? But I did want to just mention them because I did look into them and they are quite useful. So there's three of them. The first two are AWS SQS and AWS SNS. So I'm sure many of us have looked at these. Personally, a question which I've always asked myself is like, hey, what's the difference between AWS SQS and then Kafka, right? Like, should I use SQS or should I use Kafka? Like, I've always preferred SQS just because, it's like fully managed for you. It's pretty simple. But then also I've always wondered, like, do I need some of the features that Kafka provides, which SQS doesn't have? So I looked into that and then I came up with an answer. But first, let's go over what SQS is and what it does. So Amazon SQS is the full name is Simple Queue Service, and it's actually one of the oldest services in Amazon Web Services. So in AWS, I think the oldest service is like EC2 and then like S3, and then like the second or third or fourth one is actually SQS. So it's actually been there since like 2005 or earlier. What it does is that it gives you a queue abstraction. So it's a distributed queue. So you can have a producer. It's going to be writing messages onto the queue, and then you have like one consumer type. So you can have like multiple consumers, but they all are basically the same code, right? So you have one consumer type, which is consuming from the queue, processing the queue messages. One limitation is that you cannot fan out to multiple consumers, right? So in Kafka, you can like fan out, but here you cannot do that. And yeah, so that's one downside. It is pull based, so it's going to be pulling messages. It's not going to be push based. But it is fully managed. It is serverless, pay-per usage. I think it's good for use cases where it's like you have like one producer, one consumer, you need to send some data. If you need like fan out, or if you need to have like multiple topics, then SQS might not be the best fit. For that, you can look into SNS. So Amazon SNS is Simple Notification Service. It's a pub/sub system, and so by pub/sub I mean that SNS is going to be responsible for delivering messages to your consumers. So SNS will support over 12 million consumers at a time. It's going to be storing the state for those consumers in memory. And so whenever you send a message to a SNS topic, it's going to go and deliver those messages to all of those consumers. So what type of consumers does it support? So it supports like calling HTTP endpoint, it supports triggering a Lambda, it supports publishing to a SQS queue, and supports many more. So it's basically like a pub/sub system. Just as like in Redis, there's like Redis streams, which is like pull based. It's like the SQS equivalent. And then you have Redis pub/sub, which is like similar to SNS, which is like a pub/sub system. So you'll see that differentiator a lot, I think. But yeah, and SNS also has fan out. So you can, let's say you want to send one message and you want to broadcast it to like 100 different consumers, you can go ahead and you can do that. So yeah, that's SNS versus SQS for you. Okay, this is the last slide because I know I've been talking a lot. You guys are probably a bit tired. Okay, yes. Okay, so before my conclusion, I had one more slide. Okay, here it is. So there's another service which I would highly recommend everyone check out, which is called nats.io. So this is basically a single binary without any dependencies. So like we've looked at like systems like Kafka and Pulsar where they need to store their state in Zookeeper, but here you don't need to do that. So you just run a single binary. You can actually even embed it inside of your Golang program to set up like a service bus in memory, or you can run it as a server. It supports both push and pull, pretty easy to work with, and you can scale it pretty easily, pretty trivially by adding more NAT servers to your mesh. So yeah, I've worked with it just locally, works pretty well. There's no persistence in NAT's core, but Jetstream is a module that they have which adds persistence and adds many other features as well. So do check this out if you have time and interest. So, okay, so, we went over a ton of content today. Hopefully it wasn't too boring. I know it's, quite theoretical. So, yeah, but in conclusion, we talked about the important design decisions that we need to make when looking at different message brokers. So we went over 10, both on a single node and on multiple nodes. So things like what data storage is in use, what metadata storage is in use, what compaction strategy is there, what does the producer do, what does the consumer do, what's the interface. And then we went over the design decisions for multiple nodes. So what's the replication strategy, what's the partitioning strategy, how do we avoid hotspots, how do we handle network partitions. And then we went over a couple of different message brokers in details. We went over Redis Streams, Apache Kafka, Apache Pulsar, and then we went over SQS, SNS, NATs, and then we talked about the important design trade-offs between each of them. So yeah, hopefully talk was useful. I think it was pretty theoretical, but hopefully, it was useful, and I'll provide the slides as well. So yeah, that's all. Thanks everyone for coming.